Hello everybody, I just thought this would be interesting.
But I've never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
And you can take it out on the street.
Taking it out on the street.
I'd possibly interview you guys for about a minute. We're doing a science experiment.
What I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
The obvious thing you think you're going to see is you're going to see two lines.
2 lines on the bottom of the box. 2 bright bands.
Yeah, I think it'll be one line for 2.
I could expect the whole box lit up.
Kaleidoscope of some sort.
A bunch of colours.
Probably, yeah.
Rainbow? Colours?
There, have a look. You expected to see kind of one line. Is that what you see?
No,
I see dots.
How many?
it's one circle.
Oh, there's one in the middle strongest, 2 either side.
Two on the outside of multicolored, on the middle, it's just white.
Out of a rainbow.
The rainbow colour as well. Quite a few colours, but lots of little dots.
But there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from 2 slits. That's incredible.
So all we're doing is we're putting light through 2 very narrow slits side by side. How does this make any sense?
There's some kind of principle involved there. The average person's not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see 2 bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have 2 sources of ripples, which are basically like the 2 slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the 2 sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere, and you wouldn't see any light there. It's light canceling itself out.
It's basically the same as like having 2 drops of water fall in a swimming pool. Exactly the same
And then they go
pattern.
and overlap. As this ripple overlaps those ripples,
Yeah.
down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and a bright spot, and a dark spot, and a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as you go further from the central maximum. So you saw the ones to the right were slightly colored.
Yeah,
That's
it's
because
like
the reds are going to meet up at different places than the blues.
and that's all that makes the colour differences in different wavelengths.
Exactly.
That's amazing.
So the difference
So
between
there's
red
so
and
that,
blue,
that red bit over there, the green part is just I'm seeing
It's a
that it's
different-
just different
different
wavelengths, and that's how we bring in all these different colours all around us. That's amazing. I'm amazed. Oh, good on you, thanks, Ben.
Hey, thank you.
I have been enlightened, literally.
Dramatically, it alters our picture of reality by carrying out a similar experiment, not on the scale of tiny particles, but on the scale of more ordinary objects, like those you find here in bowling alleys. First, I need to make a couple of adjustments to the lane. You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen back. And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit. The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller. You can picture them like this. Let's see what happens if I throw a bunch of these balls. When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you'd think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing. Waves. Waves do all kinds of interesting things. Things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others. Sometimes, they cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes in what's known as an interference pattern. So, how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
Particles are particles, waves are waves. How can a particle be a wave? Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave. A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles. And rocks are not waves. Rocks are rocks. So a rock is an example of a particle. An ocean wave is an example of an ocean wave. And now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow the electron got smeared out and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described. Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave. That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electron is. That's where the electron is most likely to be.
And that's just very strange, right? So the electron on its own seems to be a jumble of possibilities.
You're not allowed to ask, where is the electron right now? You are allowed to ask, if I look for the electron in this little particular part of space, what is the likelihood I will find it there? I mean, that bugs anyone. Anytime
As weird as it sounds, this new way of describing how particles like electrons move is actually right. When I throw a single electron, I can never predict where it will land. But if I use Schrodinger's equation to find the electron's probability wave, I can predict with great certainty that if I throw enough electrons, then say 33.1% would end up here, 7.9% would end up there, and so on. These kinds of predictions have been confirmed again and again by experiments. And so the equations of quantum mechanics turn out to be amazingly accurate and precise, so long as you can accept that it's all about probability.
Is responsible for many important phenomena such as the alpha decay of atomic nuclei and the operation of certain types of diodes. Yet quantum tunneling is completely contrary to our intuition about how the universe is supposed to work. This is because quantum tunneling has absolutely no analogy in classical physics. To understand quantum tunneling, we must understand that particles don't have a defined position until they're observed. Instead, all particles are described by what we call a wave function. The probability of a particle being observed at a particular location is given by the square of the amplitude of the wave function at that location. In this example, the red sphere represents the most probable location where we'll observe the particle, because this is where the amplitude is greatest. Suppose that the particle bounces off a barrier, where the energy of the barrier is greater than the energy of the particle. This is represented by the wave function reflecting at the boundary. Let's take a look at how the wave function behaves inside the barrier. As the distance into the barrier increases, the amplitude of the wave function decreases exponentially. But the wave function doesn't actually reach an amplitude of 0. Now, let's consider a new scenario where the barrier is shorter in length. As before, amplitude of the wave function will decay inside the barrier. But since the wave function doesn't reach an amplitude of 0, the wave function can exit the barrier on the other side. Once the wave function exits the barrier, its amplitude no longer decays. A portion of the wave function passes through each of the two boundaries. And a portion of the wave function also reflects at each of the two boundaries. This means that there is a certain probability that the particle will pass through the barrier to the other side, and a certain probability that the particle will bounce off the barrier. If we send a number of these particles towards the barrier, some of them will pass through and some of them will bounce off. If we send a number of these particles towards the barrier, some of them will pass through and some of them will bounce off.